Good morning. Today's challenge is the second Newton's law. And the second Newton's law says that if all forces are unbalanced, the forces acting on the object, then the object will move in accelerated fashion. From the first Newton's law, you learned that if object is not moving or moving with constant velocity, then the two forces, or all the forces acting on the object, are balanced. And balance means if you add them together, they will equal to 0. So these two weights suspended over the pulley by a black string experience forces. And since they're at rest, we can deduct that these forces are balanced. So what are the forces acting on my left weight? That will be force of weight. That will be mass times gravity, right? And it's not falling down because another force of tension, is pulling up. Force of tension, right? They're absolutely equal, and when we add these two forces, it results in 0, and that's why object is at rest. It will be the same relationship if the object is moving with constant velocity. How would we know that object is moving with constant velocity? It will cover equal interval of distances over equal intervals of time, and we can always check that. For that, we will need a ruler, and we will need a clock or time measuring device. Now, in here, you see that you have two blocks, and each of them is experiencing equal tension, which means they're experiencing equal gravity, right? And masses are equal to each other. Now, what will happen if I replace one of the weights with smaller one? Can you predict what will happen? Say I take off my left weight and replace it with smaller. What will happen? Well, what I expect to happen is that my weight will become smaller, right? Right? And if tension is the same, then my object, the light object, will move up. Why? Look, if tension is the same and the weight is smaller, if I add these two forces, my resultant force will be up, right? And when object is acted upon force in certain direction, starting from rest, it will move in this direction. And it should be accelerated motion. We can check that. We can check that in equal intervals of time, the distances covered will be greater and greater and greater every moment of time. The reality is, though, our tension will also be smaller. It won't be equal to the previous one. It will shrink a little, not quite, not to be equal to the small weight, but it will, become smaller, right? So if I have same weight acting on my right weight, but smaller tension, if my force down is greater than my force up, my overall motion will be down. And in here, my overall motion will be up. I know you could say so in no time. I'm just trying to uncover why is it happening, how physics explains why the light object will go up and the heavy object will go down because of balances of forces. The task of this lab will be to figure out how difference in masses affects your acceleration. So what you have to do is to change masses. You have overall 5 different masses, right? You have 5 different masses. It's 20 different possibilities for you to try. You don't have to do all 20. But please select, reasonable number. It's up to you. And I hope other team members select another set of weights. So altogether, you will be able to find the correlation between difference in mass and the overall acceleration. How would we do the experiment? Of course, if our masses are equal, there is nothing to measure. It will stay this way forever and ever. But if your masses are not equal, and I promised to replace this weight, so I'm accurately replacing it with a smaller weight, and I expect the heavy weight to go down in no time. Now, my heavy weight will go down. And for me to have more time to record my motion, guess what? I need to provide this heavy weight with a greater distance to start with. So what I will do is I will bring my weight as far as possible, and I will take care of the bottom of the thing. So I will be measuring always the bottom of my weight in the recording. So I will zoom it in and measure. For us to see where it goes, see, I have 5 centimeters here, 10 here, 15, 20. So we will see the distance covered. And I will try to start my upper weight from the same position at all times. If I have time to invest into that, I will create a launching mechanism. But I know you're busy and it's summertime and you want your time to be filled with sunshine and swimming pool and joy and friends. So it's okay to take this small thing. So next thing that you need to do, once you put it in a launch position and it's at rest, that's very important. next thing that I will do, I will start the timer. And it's okay if the timer will run from 0 to something else. From each frame, the slide that I will be watching, I can detect the position and time and plot the graph. Do you think it will take 1 second, 2 seconds, or fraction of a second for the object to go down? What do you think? Let's try. Aha! What we've experienced is mishap. And I'm glad it happened, because it teaches me something. What does it teach me? That I need to be aware that when the weights are moving, they can eventually collide with each other. And that is not what I want. It will kind of skew all my measurements. I don't want this to be in my experiment. So now I have to sacrifice the distance traveled to avoid these accidents. So right now I'm launching from this position. Please make sure you know what object you are detecting. And I will reset my timer. By the way, it's been a very short period of time for the launch. And it will be even shorter for our next experiment, right? So I will start. I will put it in a position and then drop. Now, with my recorded experiment, and you can stop and forward it frame by frame, I can take the measurements of where my weight was, right? So I will have measurements, and now I will produce measurements that are kind of from my head, because I know what to expect. Your measurements will be different, dependent on masses that were there. But masses play a role. So what I will put is mass 1, right? And it was, my mass 1 was 250 grams. Or 0.250 kilograms. That 0 is important. Don't skip it. That's how much you know about the mass. The smaller mass, M2, is also a fraction, right? How big is that? Let's see. It was 100 grams. Or 0.100 kilograms. Both zeros are important. Don't skip them. And now what I will do is I will record the position. And since I will be looking at the ruler, it will be easy to read it in centimeters. And I will record the time, and it will be time in seconds. And I will move my recording frame by frame to detect that in the first, say, 0.1 of a second, the object moved. It's impossible, because there are about 25 frames per second. So it will be first frame, right? 10 seconds, 0.4, whatever is your starting time. Your position will be, say, 40 centimeters, right? And then 10.08, it will go 41 centimeters. And then at 10.12, and I'm reading it from here, it will be 44 centimeters. and then at 10:16 I will have 49 centimeters, and so on and so on. So that's my measurements, the measurements that I will do frame by frame. Now, next thing that I will need will be change in position. How much did it go in here? It went 1 centimeter. How much time passed? 0.04 seconds. Now, you don't need to put your units in the thing. I'm so accustomed to put units with every number, it comes automatically, but it's not required. Next time I will go 3, right? And it will be 0.04 again. Well, since I'm making up those numbers, I'm trying to make it equal intervals. Chances are when you will stop the frame or fast forward the frame, you will get not equal intervals, and it's okay. Because next thing that you will do after you measure your that will be your start time, and that will be your start position. So we will measure then distance from the start. That will be 4, right? That will be 9. And in here, the first one was in 0.04 seconds. The second, I subtract the first one, and it will be distance 4, and I subtract 10:04 from 10:12, and I will have 0.8 seconds. And then I subtract here, and it will be 9 centimeters in what? In 0.12 seconds, and so on. I will have more, as many as I can, as many frames as I will be able to detect. I will check my position of a certain one weight. Why is it not important to look at the other? If you have time, please do so, because then you will know for sure that you've done a great job. Again, physics is looking for the way on how to check yourself. Not how to rely on other people, like instructor or team members, to check your work, but how to check your own work and be confident in what you're doing. That's very good skill. But it is expected that since two weights are connected with each other, both will be traveling with the same acceleration. And no, it won't be gravity acceleration. No, why? Well, because it will travel with gravity acceleration in absence of tension. Tension slows down your motion. How much? That's for you to discover. You need to figure out mass 1, mass 2, and acceleration. Okay? That's the task for this lab, and I hope it's clear. You change masses and you do your measurements again and find your acceleration. Now, your analysis should come up with the following table. Mass 1, mass 2, of course in kilograms, acceleration. Okay. What you will be submitting to me is a table. A table, mass 1, mass 2, acceleration. You can do that as a team, you can do that individually. Now, let's do it individually, unless you don't have a kid and would like to help someone. Now, let's do it as individuals. And let's measure acceleration for certain masses. And I will check that, okay? Because there is a certain acceleration, and I can predict that. And you can calculate it as well. It will be covered in the lecture class. Thank you.